Hello, vintage computer friends. It's been very quiet on my YouTube channel in the last 4 to 6 weeks, and I wanted to give you an update of what I've been up to in the meantime. So it was partially quiet because I was on travels, right? And I went to Germany, my original home country, and from there I retrieved my original Busch 2090 Microtronic computer system. And as you see, I mean, there isn't much left of it, right? So it's only a bare bones PCB at that point, right? And as you know, I'm a big fan of this 1981 4-bit educational computer system, which was my first computer on which I learned the basics of programming, well, machine language programming. And I got this in December 1983 from my parents. So yeah, I retrieved it from my storage in Hamburg in Germany, and I brought it back to California, where I'm now, right, which is my home since 2010. But originally I'm from Hamburg, Germany, and this is where I still have the storage. And I brought it back with me for a reason. And given that I, have a number of 2 or 3, actually I have, I think, 4 fully functional and fully assembled Microtronics, right? And they all look much better than this one, but this is really the original, which it all started for me and which basically launched my career into computer science. So I'm emotionally attached to it. And given that it only has the bare PCB left, it wasn't very useful, right? So I wanted to save it basically and use it again because it was my original computer, so I'm attached to it. But in order to make it useful again, I had to do some repairs and upgrades to it. So one thing, for example, was without its console, right? It basically had its calculator keypad hanging in the air here, right? So you couldn't really type like this, right? And so this is basically just like the old Texas Instruments TI LED, bubble LED calculators, TI-30 or so from the late 1970s, early 1980s, right? This this kind of keypad. So first order of business then was to actually make a external keyboard so that I could actually use it again, right? And I connected it here over the pin header. So I removed that original calculator keypad. Also the display, right? As you see, it really needs basically like a lens filter, this red plastic here, in order to make the LEDs have a good contrast. Otherwise the readability is very low, right? So the original display I removed, you can see that here, and the reason I removed is that the lens filters were originally in the console, and the console I don't have anymore. So in order to actually mount lens filters on top here, it's not really easy, right? Because there's no ridge to which you can glue them on, right? Unlike this one here, right? Which basically has a ridge basically onto which I then could just glue these lens filters, right? Using just Gorilla second glue, right? And so that's what I did here then, right? So I gave it a new LED 7-segment bubble LED display, right? You can get these from Jamaica, still new, and they are compatible to the original TI ones, right? So that is called TIL 3936, yeah, 3936, and the Jamaica one is pin identical, right? So I put that in there, also with a pin header here, so I can actually remove it if I want to, right? So, and that's from National something, is it National, not National Instruments, National Semiconductors, I think, made those. Yeah, so but that's working well basically. And so yeah, another reason I'm doing all this, and you see all these Busch wires and mods and all these labels, right? And that is basically the Microtronic reverse engineering project, right, which is going on here. And this is what I want to talk about a little bit, really. So that's really the main reason why I brought this bare bones PCB back, because I knew we would have to do some serious mods and work to it. for this reverse engineering project of the Microtronic. So you might ask, okay, what's this Microtronic re-engineering project about? After all, you already did one, right? So this is my re-implementation of the Microtronic. I call it the retro authentic Microtronic re-implementation. So where I even have these new bubble LED displays, right? I also made other versions with OLED displays and what have you, right? So this is my final version, and I like this one the most of all the Arduino based emulators that I created, because it's really gives you a retro authentic look and feel like the original. And you know, it's also kind of portable, so you can take it with you. So here it's running the NIM game, right? So but it really, in terms of look and feel, it's very authentic to the original Microtronic. And so it is basically really a complete new implementation of the Microtronic, right? And ideally, of course, if you had the firmware, you could just emulate the CPU basically, right? In this case, it's a TMS 1600 CPU and run the original firmware. But I never thought it was possible to actually retrieve the original firmware, right? So this is just an Arduino program here which emulates everything, right? So basically the 80 mega AVR chip, so just a 328p, the standard Arduino Uno R3 chip, right, is here basically, right? So it's basically just a an Arduino implementation. And so yeah, all of this changed basically my view that, you know, that is the only way of recreating the Microtronic is to re-implement everything like on a new microcontroller basically. All of this point of view changed when I acquired a Science Fair Microcomputer Trainer. Right, and oops, doesn't fit into the camera. There it is, and I had 2 videos on my YouTube channel about it by now. And so its brain here is also a TMS microcontroller, but it's the TMS 1100. Originally I thought it would be somehow the predecessor to the Microtronic, right? Because it's using the same similar idea, basically emulate a virtual machine language, right, on the TMS microcontroller. And I thought it was released in 1976, but it was actually released later than the Microtronic in 1984, as far as I know, right? Yeah, it was released in 1984, whereas the Microtronic was planned in 1979 and then I think finally released end of 1981. But basically the operating principle is very similar, right? So all the monitor program as well as the interpreter for this virtual machine language, high-level educational virtual machine language, is in the masked programmed TMS 1600, or here in the, you know, TMS 1100 microcontroller, right? Single chip computer. And so that runs the firmware, and that firmware implements the monitor program, right, that allows you to interact with the machine, as well as the virtual emulated machine code in an interpreter. Of course, it's very slow, but you know, that gives them basically the means to implement a an educational machine language which would be suitable for learners and juveniles and kids, right? So rather than programming this in TMS 1100, a native machine language, right, or TMS 1600 native machine language, you program it in that virtual emulated educational machine language, which is, yeah, much more orthogonal and easier in terms of the Microtronic. And the same holds true of the Science Fair Microcomputer Trainer. So yeah, I acquired this microcomputer trainer, right? And so I published a couple of videos about it, and then I got contacted by Jason, right? And Jason basically, first of all, he corrected me on a couple of errors that I had in this video, right? As I said, I originally thought it was released in 1976, but it was actually released in 1984, the Science Fair Microcomputer Trainer. And then he also said it transpired that they actually have an emulator of the Science Fair Microcomputer Trainer, which is not really an emulator, but which actually runs the original firmware, right? And this is Deckel's Nibble emulator. Actually, it's not an emulator, but it's a TMS 1100 emulator that then runs the original firmware, right? And I was kind of intrigued. So Deckel and Jason then basically told me that it is possible to read out the firmware from the mask programmed ROM, right? And the way to do this is that there is a little known so-called test mode. And if you put the TMS 1000 microcontroller, so any of the members of this TMS 1000 family, including the TMS 1100 in the Science Fair or the TMS 1600 here in the Microtronic, but there are also other members of this family. So you put this into the test mode, and then you can basically read out the ROM contents, right? But you have to follow a certain protocol and you need to make certain electrical connections, right? So, and Deckel as well as Jason together, so they basically have an Arduino program that allows them to read out the firmware, right? And yeah, then when I heard of this, of course I was hooked, right? Because for the first time in Microtronic archaeology, basically, there was the potential of possibly acquiring the real Microtronic firmware from this ship, right? And so far, the only methods that I knew about were based on decapping, right? Die decapping. So you grind off basically the plastic of the ship, you expose the die of the ship, and then you take pictures with a microscope, right? And from there, the bit pattern you observe in the mask programmed ROM area, from there you can actually extract the ROM content and the bin file. And Sean Riddle had done this for a lot of Texas Instruments TMS calculator chips and Speak and Spell and Simon and so on, right? And also he did it for the Microcomputer Trainer, the Science Fair. Yeah, so, but you know, in order to acquire the ROM in that way, I would have had to send a TMS 1600 Microtronic chip to Sean, and he would have to destroy it, right, in order to read out the ROM. So I didn't really want to do this, so I was super excited and to hear that there is this test mode that Jason and Deckel basically told me about, that then allows us to read out the firmware, right? So yeah, and so of course I had to do this, and what you see here is basically on our Hackaday page, right? Deckel as well as Jason are also project members on our Science Fair Microcomputer Trainer Hackaday project, and I asked them to basically you know, contribute this information, how you can read out the ROM, the firmware of the Science Fair Microcomputer Trainer. And this is the schematics that Deckel provided. So you gotta make a couple of connections here. So the whole thing is then driven, the protocol that allows you to read that out is just an Arduino here, right, or any other microcontroller. But given that the old TMS 1000 family chips are PMOS and operate at -9 volts basically, right, because it's PMOS, you need a couple of transistors basically to amplify signals, right? So this is here the TMS 1100 and the Science Fair Microcomputer Trainer. So, and what you see here is that, for example, you need to drive the clock, the oscillator 1, with the Arduino, right? And so it's under microcontroller, under Arduino control. And basically there's one digital pin 3 from the Arduino that goes then into an inverting transistor amplifier, right? That basically gives you then an oscillator clock level between, you know, closely to 0 and almost 9 or 8 volts, right? So full swing from 0 to 8 volts or something like this, right? Because yeah, this is really a PMOS chip and it's powered by -9 volts. So the way that's achieved here is just, you know, ground and minus 9 volts are basically flipped, right? So you can still power it with a standard, positive power supply, but you just swap ground and the so you swap VCC and VDD and ground basically. And so you have to control the oscillator, right, the clock, and you also have to get hold of K1, K2, K4, K8, which are inputs, and those are then used to basically drive this test mode protocol that allows you to read out the firmware. So basically you are clocking in, you are supplying the address and some other protocol information over K1, K2, K4, K8, and again those are controlled by the Arduino. 5, 6, 7, 8 digital pins and inverting amplifier transistors. They are also in the range of 0 to 8 volts and these output levels. And then the bits are coming out of the 07 pin. So 07 is basically monitored and by the Arduino then, and the incoming serial bit data is then basically assembled to give the full bytes, the ROM contents. And for this to work, you also need to basically drive the init pin. So you gotta supply 9 volts to init in order to put the chip into reset mode, basically, right? This is as if you are pushing down the reset button on the Microtronic, basically, but programmatically with the Arduino. So this is all well described on our Hackaday page about the Science Fair Microcomputer Trainer. Deckel wrote this log entry, right? And he also supplies the Arduino program, which is then needed in order to read out the ROM. And so there's one other thing that is not, I think he forgot to mention, but he mentioned it in another video, and that is you also need to put the machine into test mode. And on the Science Fair Microcomputer Trainer, this is pin R6, and actually if you look at the TMS 1100 pin out, this is really pin R10 of the TMS. So you have to connect this to 9 volts in order to drive the machine into this test mode, right? And so this was the first big problem we basically had with the Microtronic. So because it's the bigger version of the TMS, right, the 1600, which has 40 pins, it actually turned out to be not pin R10, right? And so yeah, I needed to spend quite some time. So these are the schematics of the Microtronic, until I finally found out that for the Microtronic it's not R10, but it's actually R8, right? So we have to connect R8 for the Microtronic to 9 volts to take it into test mode. So yeah, and then in order to make all the other connections, I mean, you can tell that the Microtronic is quite a bit more complicated than the Science Fair Microcomputer Trainer, and also it's on a real PCB. So I actually needed to make a lot of cuts basically on the PCB in order to cleanly isolate the pins, right? So for once, I then did see that the clock here, right, OSC1 and OSC2 it's using the internal clock crystal and not an external crystal. So there's an internal clock at 500 kilohertz, and so here's a Busch wire outside, right? So I needed to cut this trace, for example, so that I can get clear access to OSC1 and OSC2, so that the Arduino can supply the external clock to the TMS 1600. And yeah, in a similar way, you know, I needed to get access to the init pin here, right, which is, what is it, pin 17 here, right? So I also needed to make a cut here. And then we have the K inputs basically, which also turned out to be a little bit difficult. So as you can see that the K inputs here, K1, K2, K4, K8, which are really the main address and protocol driving inputs that are controlled by the Arduino, are also connected to this analog switch here, IC1416, right, which is this chip here, right. And what I was observing was that the transistor here in my circuit that is driving K8 was getting hot, as well as the 1416. And I also observed that I didn't get a clearly defined logic low level here, right? So that signal K8, there was some interference here between this 1416 IC and the K8 and the transistor, which I use then to drive it externally. So I ended up removing the chip and putting in a socket here, right? So, and now it's pulled. And so yeah, in my search for the R pins, then, you know, they said it could be anything, right? It could be R10, it could be R8, but it was also speculated that it would be R14 or R15, so I basically cut all these traces on the Microtronic PCB as well. And this is what you see all these Bosch wires for, right? Yeah, so quite a bit of hardware mods then required for the Microtronic, right? I mean, I can show you how that looks now on the back. It's not pretty, but I mean, this Microtronic, as I said, even though I'm very attached to it, and I'm super happy that it's still working after all that torture that I applied to it, it's still fully functional. So these old 9-volt PMOS chips, they are really robust, right? So here you see all the Bosch wires. So the way I did this is, you know, I cut a trace on the PCB. For example, here you can see the cut for 07, right, which is the output, where the serial bit data is coming out, right? I cut that here, and then I'm putting basically a DuPont wire here, so that way we can basically also reconnect them and splice in basically the Arduino signals, right? And yeah, so the most difficult part was really to identify the test mode pin, right? And I had a very bad feeling, you know, trying to identify this pin. So, and I actually went down basically all the pins here, right? All the R pins are here on the TMS, and I ended up using this test clip then, which is just connected to VCC 9 to 9 volts basically to hold it high. So yeah, it was also challenging to come up with a way of powering this, right? Because the Microtronic has two power levels at least, -5 volts and -9 volts, right? And so it obviously has its own power supply. And once that's plugged in, I mean, it produces the power levels that are needed. But then the Arduino has its own USB power supply, which is needed to communicate the ROM content, right, from the Arduino program, the output into the serial monitor. From there we acquire the ROM content in the console, right? And also you need to power these amplifier transistors up to 9 volts, right? So originally I had like 3 power supplies, right? I had no, originally I tried to power the Arduino as well as the transistors over the Microtronics internal power supply, right? So I would plug this in and then grab basically -9 volts and ground in order to power this here, right? And that's possible because the voltages are also supplied here over the DIL socket, which is for the cassette interface. So this has -5, 0 and -9 volts, right? So I would power the Microtronic and then use the power from there. So yeah, but turned out that, you know, we weren't getting the right ROM content, and with a lot of back and forth between Jason and Deckel, we came up with all kinds of hypotheses, right? And one was also that, you know, power levels are not good enough, so so we tried different ways of powering it. And eventually I then put, you know, the lab power supply here to power the transistors only, right? And the Arduino would still be powered over USB and so on. But in the end, we then adopted the strategy to actually let the lab power supply power everything, right? So we leave the Microtronic disconnected, right? And we just, you know, inject the power now into the Microtronic using the DIL socket. And So the lab power supply gives us the 9 volts, and this is used to power everything now, which is a clean solution, right? And yeah, so at first it didn't look very good, right? So we weren't getting basically proper ROM content, but rather so we knew that the circuit was working to some extent because we were getting back the address basically over the serial bit output from the Microtronic, right? So we knew something was working of this program, Decades and Jason's Arduino program that retrieves the ROM content, but it wasn't working correctly. And so there were all kinds of different hypotheses then, like voltage level is not good enough, right? Maybe even though this R8 test pin seemed to be the one that enables the test mode, maybe there were other modes, right? So I kept trying, looking for R7, R9 and so on, and some of those also did some interesting things, but none of them did what we wanted, right? And then eventually I also identified this electrical problem here, that this transistor was getting hot because, and I just still don't know why, there's some. So I think my hypothesis is that this 1416 chip is bad basically, and that the output basically wasn't disabled and clashed with the transistor output. I think that's the best hypothesis I could come up with, right? Because the circuit diagram doesn't really show any difference, right? The way K8 is addressed here. So K1, K2, K4 were all doing fine. Only K8 was getting hot, right? But so it's either an undocumented thing on the PCB which didn't make it to the schematics here, right? Or basically 1416 was bad. Anyhow, pulling this fixed the logic level problem with K8, and the transistor also for K8 no longer got hot, right? So yeah, after that was then all fixed, then the final thing was that we actually needed to make a few changes to Deckel's and Jason's Arduino program, and that one change that was required was that so this is only a 2 kilobyte mask ROM, right? Whereas the TMS 1600 has a full 4 kilobyte ROM. So we needed to clock and to supply the address of one more bit basically, and adjust the code to use the proper line for asserting that bit, that piece of the so-called chapter address bit, right? It's basically selecting the way that TMS memory ROM is organized is in chapters and pages, right? And each page is 64 bytes, and so 16 pages of 4 chapters of 64 bytes, making up the 4 kilobytes. And so after that, we then got the addressing right, but we still didn't get the right ROM content. And that was because there is one difference in the clocking in order to basically trigger the TMS to now supply the ROM content from its masked ROM at that address that we specified in that register. We needed to drive the clock differently. And Deckel basically figured that out. He said, try different ratios of high and low pulses, timing for the clock. And then one of these settings actually finally then achieved did the trick, and we finally had the real Microtronic firmware ROM. So that's a big step forward for Microtronic archaeology, if I may call it like that. We finally have the Microtronic firmware ROM, and that will now enable all kinds of exciting developments, right? So we no longer need basically a re-implementation of the Microtronic as a C Arduino program, but we can just use the TMS 1600 emulator and run the original firmware. So I'm very curious to see that, and that's, as I said, exactly the way that that Deckel pursued for his Nibble TMS Microcomputer Trainer, Science Fair Trainer, right? So it'll be great to also see that kind of possibility for the Microtronics. And now we actually have to understand the firmware, right? So we have the machine code bin file, and we have to reverse engineer basically the assembler code. So I'm working with Jason and Deckel in order to understand the disassembly listing, right, and see if we can understand the Microtronic firmware. So that's probably going to take a bit. I don't know anything about TMS 1000 series controller programming, right? And I think I'll probably get started with this book here, this classic Osborne 4 and 8-bit microprocessor handbook, which dedicates a chapter to the TMS 1000. So I can read about there and get myself familiarized here with the TMS 1000 family, right? Because obviously I know the Science Fair virtual machine language and the Microtronic virtual machine language very well, but this has, as I said, nothing to do with the real architecture of the TMS 1000 family, right? So I'm going to read this, and then with Jason's and Deckel's expert knowledge of TMS 1000 programming and machine language, I'm sure very optimistic that we can actually understand and successfully re-engineer the Microtronic firmware, and then maybe in a year or two we actually have a real Microtronic re-implementation that runs the original firmware. So, but as a last thing, let me actually quickly power up here and show you the process of dumping the ROM. So we turn on the lab power supply here, right, and it's actually enough to supply like 7 volts or so. Then I power up the Arduino, right, and you can tell that the Microtronic looks funny, right? So it actually came up here, and you see that given that it's not using its internal 500 kilohertz clock, but the externally supplied clock signal, how it clocks much slower here, right? So you can actually see how it's multiplexing the display. So if we had reset basically on the Arduino, right, then it initializes its pins now, right? And now, I mean, it is actually ready to, once we started over the serial monitor, right, it's actually ready to dump the ROM. And we will also get visual feedback. I said 07 is the output which retrieves the bit, right, from the ROM. And so we have connected an LED here, right? So if I start now the Arduino program, and I've now started the process, and you can see that the LED is blinking here, right? So this is indicating the bits. Also see that the Microtronic display has been turned off, right, because it's in test mode now, sending the data. And so the data arrives here in the serial monitor. And this is actually the Microtronic firmware ROM. So we can do one more round here, press enter, and there comes the data. Still transmitting. Yeah, and it's consistently the same data, right? So it's really dumping the ROM. And yeah, that's what it is. So, alright guys, I think that was a long video, and I know it was kind of messy, right? It's a lot of detail, but I'm super thrilled and excited that we finally have the real Microtronic firmware, which was lost to history, right? So, as you know, I also tried to contact Jörg Wallen from Busch, right, who was contributed a lot to this Microtronic development and the project, right? He also was developing the instruction set and so on, and so he did not have the firmware in his archive any longer, so it was really lost to history. So that's a big step to finally have the Microtronic firmware. Alright guys, thanks for watching, and I'll keep you posted. Until soon, right? Bye.